To facilitate the integration of brain-computer interfaces and the handling of commands by thought in virtual reality environments, we have created OpenViBE software. A brain-computer interface, or BCI, is a new means of communication that controls or monitors computers and machines directly using brain activity. The brain activity is measured by electroencephalography, or EEG, using electrodes located on the surface of the skull. The BCI analyzes brain signals in real time and can identify specific mental activities for use in operating a machine or computer. To use a BCI under ideal conditions and allow a user to carry out commands using thought, the position of the EEG cap is crucial. In order to place the electrodes at the precise locations required for recognizing brain activity, some measurements are necessary, as for example here for the CZ electrode located on top of the head. 2 electrodes are often necessary, one on the nose, the other on the forehead, corresponding to neutral and ground. In the following example, an electrode is placed on top of the head. Not only does this electrode detect brain activity related to executing foot movement, but also that related to imagining foot movement. To use the Force and employ thought to raise this spaceship from the Star Wars movie, the OpenViBE software will detect the moment when the user stops moving his feet. Once this significant event has been identified, the software sends the command "Raise the spaceship." After a concentration phase, the user must now only imagine that he is moving his feet. When the thought of movement stops, the signal from the EEG is the same as the one observed when real foot movement stops. The software can then send the command "Raise the spaceship" again. Since it consists of a single command, this is a one-class brain-computer interface and is in asynchronous mode since the user can raise a spaceship at will. In this second application, the EEG cap sensors are placed so they can receive signals transmitted by the brain's motor cortex corresponding to hands. This time, the goal is to send commands using EEG activity observed during left or right hand movement. After using BCI to identify the frequencies used to move each hand, the OpenViBE software can now detect a right-hand movement command that makes the ball go to the right and a left-hand movement command that makes the ball go to the left. The user can now remain motionless and just concentrate on the movement of each of his hands to control the ball using thought. This is a 2-class interface, since there are 2 possible commands. OpenViBE handles electrical signals transmitted from the surface of the user's skull. Depending on sensor location, as here for example on the right and left hemispheres, the software can link together a whole series of tasks represented by small basic blocks. The brain-computer interface uses the following signal processing logic. A data acquisition phase is followed by a signal noise reduction process. Next comes a data extraction phase that keeps only the frequency range corresponding to hand or foot motor activity, for example. At the same time, the software learns the user's different reactions to the commands that he is given. Imagine a right or left-hand movement, for example. The software will then classify this mental state and categorize the characteristics related to the user's thought. This application relies on a 3-class BCI using EEG characteristics of imagining movement of the feet, of the right hand, and the left hand. Remaining completely motionless, a well-trained user can move to the right by imagining a right hand movement, to the left by imagining a left hand movement, and move forward by imagining foot movement. This virtual museum visit application shows that the user can move around using 3 basic commands, although this can prove to be slow and tedious for long distances. The application demonstrates another problem. This type of navigation using 3 basic commands rapidly exhausts the user because of the intense concentration required to move around. We have created a new approach to navigation by thought, which allows the user to speed up his movements by using navigation points derived automatically from the scene to be crossed. With this system, the user must select the blue or yellow points that he wants to reach, while imagining left blue and right yellow hand movements. Once a point has been selected, negotiating the way to the selected point is automatic. Imagination of feet movements can quit or cancel the point selection. OpenViBE is a software platform for designing, testing, and using brain-computer interfaces. It is software for real-time processing of brain signals and can be used to acquire, filter, process, classify, and visualize brain signals in real time. OpenViBE is a library of functions written in C++, which can be integrated and applied quickly and easily using modules. The platform's main advantages are modularity, portability, availability of different tools for different types of user, programmers or non-programmers, superior code performance, and compatibility with virtual reality technologies. The graphical user interface is simple to access and very easy to use for creating BCI scenarios and saving them for later use. In OpenViBE Designer, the available functions are listed in the right-hand window. The user simply slides and drops the selected functions in the left-hand window. He can then connect the OpenViBE boxes together to create a scenario and processing step successively. Lastly, he just presses the play button to start the application and run the BCI. The software also offers many 2D and 3D visualization tools to represent brain activity in real time. It is compatible with many EEG and MEG type machines because of its generic acquisition server. OpenViBE offers many pre-configured scenarios for different applications, including mental imagery, neurofeedback, P300 signals, etc. OpenViBE is open source and available free of charge on the Inria Forge. Don't hesitate to download OpenViBE and give it a try.